Welcome to my YouTube channel. In the last lecture of matrices, we have discussed matrix addition between two matrix, multiplication between two matrix, and scalar multiplication of matrix. That is one scalar and one matrix. How we multiply. So today I will discuss matrices and some properties and some special type of matrix. Here is one theorem. Given that A, B, C are matrices, then whenever the products and addition are defined, this following are true. A into B into C is equal to A into B into C. Whenever this is possible and this is possible. So we know that A and B, if A is M cross P and B is Q cross N, so this multiplication AB is possible only if P equal to Q. So that's why in the theorem it said that if whenever the products are defined, so products defined and sums are defined when A and B, A plus B is defined when A and B have the same order. So basically we can take ABC square matrix, but other than square matrix it is possible. So we will discuss what is square matrix. So let first discuss the theorem. So if we multiply A and B first and then C, then we get the same result as we multiply first B and C and A. So this is A into B plus C, and it can be written as A into B and plus A into C. If this multiplication, this is called left distribution law. So left distributive law, as A is multiplied from left side, and this is right distributive law, as A is multiplied with B plus C from right. So B into A and C into A. So this equal to this. And K into AB can be written as K into A into B and A into KB. And 0 into A equal to 0, B into 0 equal to 0, where 0 is the 0 matrix of the order, so that we can multiply with A. So this is the theorem. This is very important for future study. So just remember this. Now we discuss transpose of a matrix A. Transpose of a matrix A is obtained by writing its columns as rows. So basically a matrix A11, A12, A21, A22, if this is a 2 cross 2 matrix A, then A transpose denoted by AT is defined as, so obtained by writing its column as rows. So we write this column as row. This is C1 and this is C2, the first column, second column. To find transpose, we have to write C1 as R1, that is A11, A21, and C2 as R2, that is A12, A22. So this is the transpose. So if this is a 2 cross 2, so this will be also 2 cross 2. So if a matrix M cross N, so its transpose will be M cross M, as rows becomes column and column becomes rows. So this is the transpose. So now we will discuss one theorem related to transpose. So to find transpose, simply we have to write column as rows and rows as columns. This is the theorem. Let AB be matrices and K be scalar. Then whenever product and sum are defined, we get the following results. Transpose of A plus B is separately A transpose plus B transpose, and transpose of a transpose. So if we take transpose of A and then again transpose the transpose matrix, then we get the original matrix. That's why transpose of A transpose equal to A. K into A transpose equal to K into A transpose. K is a scalar. It will remain same. AB transpose equal to B transpose A transpose. So transpose of product is the product of transposes but in the reverse direction because of the order. How? If this is M cross R and B is R cross N, so A cross A into B can be multiplied as R equal to R, that is MR. So A transpose become R into M and B transpose become N into R. So if we multiply B transpose into A transpose, then it will happen. But A transpose R into M and N cross R cannot be multiplied. So that's why this results happen. So this is the result, very important result. Just remember, you can note down. Now discuss the square matrix. Square matrices. A square matrix is a matrix with same number of rows and column. So if a matrix have n rows and n column, so this becomes square, as this will n rows, so this distance n and n columns, this will be n, so it look like a square. So that's why called this is a square matrix. Or rectangular matrix is like this, m cross n, so m rows and n columns, so this will look like rectangle. So whenever square matrix come with order n is called square matrix or n square matrix. So n square matrix means a matrix with n rows and n columns. So when a square matrix come in the picture, there is diagonal element of the square matrix, trace and also determinant. So now we will discuss all of that. If A is n cross n matrix, so this is 1 1 1 2 dot dot A 1 n, so in its column this is 2 1 2 2 dot dot A 2 n, and this will nth row, that is A n1 A n2 dot 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 A n. So that is first row, second row dot dot dot, this is nth row and this is first column, second column dot 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 nth column. So this is n cross o, nth row, nth column. And these elements are called diagonal. So these are diagonal of the square matrix. So Aij, whenever this I equal to j, that is Aii element are called diagonal element of the square matrix. And trace defined as TR of this matrix n cross n is the sum of diagonals, that is a 1 1 plus a 2 2 plus dot 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 plus a n n, that can be written as summation I equal to 1 to n aii. So this is the trace. So regarding trace, there is a theorem, and also square matrix has determinant. If A is n cross n matrix, that is square matrix, then determinant denoted as this, and we will discuss how to find determinant of a square matrix. So now we focus on matrices. So let's take a theorem on trace. So this is the theorem. Suppose A and B are n square matrix, that is n cross n, and B is also n cross n matrix, and K is a scalar. Then trace of A plus B is trace A plus trace B. Trace of A transpose is the same as trace of A. Trace of K into A equal to K into trace A. And whenever product, so trace AB equal to trace BA. So as like transpose of AB equal to transpose of B into transpose of A. So similarly trace AB equal to trace B into A. So trace of this product same as trace of this product. So this is the theorem. So now we take one example to verify this one, and this is obvious because whenever we transpose a matrix, so aii remains same in this matrix also. So whenever we find transpose for a matrix, This is sum of AII, and this also becomes for A transpose. So trace will never change for A transpose and A. And for K, so if we common first K and then trace, this will be equal, and also if we trace, this will be KII. So this can be written as K into summation AII. So from this we can prove this. From this we can prove this. And this is a theorem. Just remember this. If needed, we will prove this. So just we take one example to prove this. So two matrix same order given. First we find A plus B as definition of addition of matrix. We get this plus this, that is 3. This plus this, that is minus 3. This will be 4, and this will be minus 4, minus 1, minus 4, minus 2, minus 6, and this will be 5, 1, 6, 6 to 8, 7 minus 4, 3. So trace A plus B is 3 plus minus 1 plus 3, that is 3 minus 1 plus 3. So this will be 6 minus 1, that is 5. And trace of this matrix is 1 plus minus 4 plus 7, that is 8 minus 4, that is 4. And trace of this matrix B is 2 plus 3 minus 4, that is 5 minus 4, that is 1. So trace A 4, trace B, trace A plus trace B equal to 4 plus 1 equal to 5, and this is trace A plus B. So this property holds. This is happen because of the definition of trace. So we have to add this, add this, add this. So this will come in trace A, and this will come trace B. So that's why this is happen. So this is a simple example. You can follow this. Now we discuss identity matrix and scalar matrix. N square identity matrix or unit matrix denoted as IN is the n square matrix with 1 on the diagonal and 0 elsewhere. So if we write 3 cross 3, so all diagonal element is 1 and elsewhere 0. This is called identity matrix of order 3. So for any identity matrix I, A into I equal to I into A remain same as A if this multiplication is happen. And scalar matrix, whenever we find K into A, so this becomes K 0 0 0 K 0 0 0 K. So this will be scalar matrix. Scalar multiplication of a identity matrix is called scalar multiplication. From this concept, we can define invertible matrix. Kronecker delta is a very interesting things defined as delta ij equal to 0 when I not equal to j and 1 when I equal to j. So exactly in identity matrix, let us take I3, that is 1 0 0 0 1 0 0 0 1. So whenever I equal to j, the quantity is 1 and other is 0. So this is as similar as this Kronecker delta. So I n can be written as Kronecker delta. So this is special case. So now we discuss invertible matrix. So we see that A into identity matrix and identity matrix into A equal to A. So here I is the multiplicative identity in matrix multiplication. And invertible matrix, what is invertible matrix? A matrix A is said to be invertible or non-singular matrix if there is a matrix B such that A into B or B into A equal to I. So generally B is the inverse of this matrix A. Simply, or we can define invertible matrix as whenever the inverse of a matrix exists, then we call this is invertible matrix, or if inverse is not exist, then we say singular matrix. So here B is nothing but A inverse. So this is B is the multiplicative inverse of A. If this exists, then we say A is invertible matrix. So for finding A inverse, we have to get determinant of A non-zero, as A inverse equal to adjoint A divided by determinant A. So this is the rule. So adjoint we define it later when we talk about determinants. So whenever determinant of A not equal to 0, then A inverse exists. From this we can say A is called invertible or non-singular if and only determinant of A not equal to 0. So this is the simple form of the definition. So now we discuss diagonal and triangular matrix. So a matrix D is called diagonal matrix if all non-diagonal element is 0. So diagonal matrix are simply this D11, D22, dot DNN. This will be a square matrix obviously. If the matrix is square matrix, then diagonal element exists. So then diagonal matrix exists. So whenever the all non-diagonal element is 0, only diagonal elements are non-zero, then the matrix is called diagonal matrix. And if below the diagonal all entries are 0, if these all entries are 0, these are non-negative elements, so we call it upper triangular matrix. And if above the diagonal all elements is 0, these are non-zero element, then we called lower triangular matrix. So this is diagonal, so diagonal matrix can be written as diagonal D11, D22, Dnn. So for this lower triangular matrix, all Aij, whenever so j greater than I, this will be 0, and for this Aij equal to 0 for I greater than j. So here these are all I greater than j for this element. So when this is happen, so upper triangular, and in lower triangular matrix this happen. At the last of this lecture, we will discuss symmetric matrix and skew symmetric matrix. A matrix A is called symmetric if A transpose equal to A, and that is for all symmetric element Aij equal to Aji, this will be satisfied for the symmetric matrix. Whenever A transpose equal to A, we call A is a symmetric matrix. And skew symmetric matrix, whenever A transpose equal to minus A, this will be A transpose matrix. So for this, Aij equal to minus Aij, sorry, Aji. So for Q symmetric matrix, Aii equal to minus Aii, so this is implies 2Aii equal to 0 implies Aii 0. So for skew symmetric matrix, diagonal elements must be 0, and for this Aii equal to Aii, this is obvious case. So symmetric matrix, whenever this happen, A transpose equal to A, if A transpose equal to A, this matrix is called symmetric matrix, and whenever A transpose equal to minus A, this will be skew symmetric matrix. So skews, in the case of skew symmetric matrix, this will happen for the diagonal elements, it will be satisfied, and from this we get Ai equal to 0. That's why diagonal elements must be 0 for the case of skew symmetric matrix. So that's it for the matrices. After that we will discuss determinant and elementary row operations or something like that, to enter how to solve system of linear equations. For today, that's it. If you like it, please subscribe my channel and share with your friends. It will be very beneficial for the students of IIIT Bhagalpur. Course is MA 101. So BTech first year students of IIIT Bhagalpur, it will be very beneficial for you and for your friends. So share with your friends. Thank you very much. मिलते हैं अगले लेक्चर पे. धन्यवाद.